Howdy, howdy, howdy. Welcome to another exciting, enthralling video that would definitely help you out in the laboratory, or at least getting started in the lab. Yeah, but also in theoretical chemical calculations, quantitative stoichiometric amounts, because so much of chemistry is done in water, in the aqueous phase, we say. We need a common way to describe how much chemical is in the water. And that most common way is called molarity. Now that we know about moles, do you know about moles? Have you watched my mole video? What is a mole? A mole is a way of counting numbers of particles. So more moles, more particles. Molarity is has a pretty simple definition. It can be tricky, but very useful in practice. It's called moles of solute divided by the liters of solution. So I could say that battery acid is fairly concentrated, but stomach acid is not very concentrated because it's watered down. I could say that orange juice concentrate from the grocery store is very concentrated. You should try some straight up if you never have. You'll pucker with it's very tangy and sweet. But you want to drink water afterwards because it's so concentrated. But if you water it down, what is it? 3 cans of water to 1 can of orange juice concentrate. Once it's watered down or diluted, it's not nearly as potent, but it's actually a little bit tastier. Or take the Great Salt Lake, for example. Great Salt Lake's fairly concentrated in salt water, whereas if I just put a dash of salt in a liter of water, that would not be very concentrated. But we need a numeric, quantitative way to describe that. So I take the number of moles of sometimes solid, I call it solute, that's the stuff that gets dissolved in the water, divided by the number of liters of solution, which technically may be slightly different or maybe largely different than the number of liters of water. If we're very concentrated, we have a whole bunch of solute and not much water. But if we're pretty watered down, then we have a little bit of solute and a whole bunch of water, which is mostly the volume of the solution. In shorthand, moles per liter, capital M, molarity. So if I had some hydrochloric acid that was 3 molar, that would be 3 moles of HCl per liter. I wouldn't even necessarily have to have a full liter. Maybe I only have a half a liter. If I had a half liter of this liquid, that would contain 1.5 moles of HCl, but 1.5 moles divided by 0.5 liters still comes out to 3 molar. Or if I had 2 liters, then I'd have a total of 6 moles. 6 moles divided by 2 liters comes out to 3 molarity. 3 molar HCl. What if I had a tenth of a mole of copper sulfate, pentahydrate? Well, that would mean half a molarity, half a molar, a tenth of molar. What if that would mean, a tenth of a mole of that salt per liter of solution, which wouldn't be that much of that salt. I don't know how many grams it would be. I'd have to do a little conversion. I'll show you one of those in a second. But if you know how to change moles to grams, you already know what I'm talking about. What if I had 4 moles? That's 4 times Avogadro's number. That's 4 times 6.02 times 10 to the 23rd particles of sugar in 2 liters of solution. That would come out to a 2 molar solution, because 4 moles divided by 2 liters is 2 molarity of sugar water. It's amazing how concentrated sugar water can become. Sulfuric acid also can become fairly concentrated, much more than this, but if I had 10 moles of H2SO4 in a total of 5 liters of solution, that looks like about 2 molar, which would be more dangerous than 1 molar, which would be a lot more dangerous than 0.1 molar, which would be a lot more dangerous than 0.00001 molar. The more watered down, the less the molarity number, the more dilute and the more I guess I could say the more innocuous, the more harmless it would be. Hard to say if an acid's ever harmless, because it could do some damage to your tissue. Always wear safety glasses in the lab. What if I had 0.084 moles of potassium carbonate, 3 liters of water? That would be division. I need a calculator for that. But anyways, it's 0.028 molar. Or sometimes we'll even describe the numbers in millimolar. A milliliter is a thousandth of a liter, so a millimolar is a thousandth of a molarity. And so sometimes we'll see it like this. 28 is easier than writing 0.028 because we're lazy sometimes. Sometimes we'll do this division. If I know the millimoles of chemical in milliliters, The millis cancel. This milli cancels that milli, and I still have moles per liter. 55 over 550 comes out to 0.1 molar potassium permanganate. Let's see. Oh, here's a tricky one. What if I had 57.2 grams of salt into enough water to make 750 milliliters? Which would indeed be very close to 750 milliliters of water, but it might be a little bit less because this solid salt does take up a little bit of space. So I do the conversion, 57.2 grams, 23 grams per mole for sodium, 35.5 grams per mole for chlorine, and this denominator is 58.5, and I would take the 57.2 divided by 58.5. The moles in that case came out to 0.978. Then you just divide by the total liters. Since this was in moles, I should have this in liters, so I took this 750 milliliters and moved the decimal 3 places left. So moles per liter is molarity, and it comes out to, when I do that little division, 1.30. Oh yeah, this has 3 sig figs, this has 3 sig figs, so I kept 3 sig figs in my answer by making sure I listed a 0 on the end of that. This comes out to 1.3 exactly in your calculator. Alright, let's do some more tricky ones. 15.8 grams copper sulfate, pentahydrate into 2 liters of solution. What does that look like? Well, 15.8. Let me change grams to moles. I put the grams on the bottom, the moles on the top. Do you remember where I got the 159.6 number? That was 1 copper, 1 sulfur, 4 oxygens, and 5 waters. Add all those molar masses up. It comes to 159.6 grams per mole. So if I change grams to moles in the numerator, in the denominator I just divide by 2 liters of solution, do that little division on a calculator, and voila, I have the molarity of that copper sulfate aqueous. Another way to say it would be 0.0495 moles of copper sulfate pentahydrate per liter of solution. Even though I did have 2 liters total, I guess that would be twice that number of moles of copper sulfate pentahydrate total. But the most important question is, what's the concentration? How much per liter of solution do I have of that solute? Here's a very important realization then, kind of from the definition. If I have molarity and if I have a volume, I can multiply those two to find the moles of solute in my particular sample. What mass of sugar is contained in, oh yeah, that's sugar, did you know that? In 125 milliliters of 0.942 molar sugar aqueous solution. So these two equations are super helpful. Super helpful. And that is molarity times volume gives moles, or molarity times milliliters gives millimoles. Yeah, and because the liters cancel and millimoles. But anyways, let's practice a couple of those. You should memorize. I'm going to say memorize this. You need to know it. Use it in the lab all the time. We'll use it a lot later. We'll use it a lot later in Chapter 10 at the latest. But before then also, I think, what mass, here's the same question. So the moment I see a molarity and a volume, I multiply them. So take this number times this number to get the moles of sugar. Or if I neglected to change milliliters to liters here in the volume, my millis would have survived the little calculation that I have millimoles. Yeah, so let's see, what would that mean? Oh yeah, so if I had 0.11775 and I saved too many sig figs there's only 3 sig figs, but I'll save to round until the very end. I can convert grams to moles to grams and find out how many grams. The original question was, what mass of sugar is contained in that sample of sugar water? And so I changed the moles into grams, 12 carbons, 22 hydrogens, 11 oxygens, 342.2 grams per mole. The moles go on the bottom of this conversion factor to cancel. Multiply those two numbers, 40.3 grams of sugar. Let's try another one. Let's see. How would you make a 250 milliliters of a 0.873 molar sodium nitrate solution? By the way, sometimes you're told what the molar mass of the salt is, the solute, so that saves you some time. So I'll just tell you 85 grams per mole. Again, as soon as I see a volume and a molarity, I multiply them together. Here I got millimoles, but I thought to myself, I don't know. If I want to know how to do this in the lab, I might not want to know millimoles because my scale doesn't read milligrams, which is what I would get if I didn't get rid of the millis. So I took the 218.25 millimoles into, move the decimal 3 places left to get the regular moles. Well, what would that moles of sodium nitrate look like? Change grams to moles. 85 grams per mole was given to me. The moles go on bottom. Multiply these two numbers. I get 18.5-ish grams, 18.6 grams of chemical. So I'll weigh that out on a scale, dissolve it in a little bit of water. Don't really matter. Doesn't really matter. I don't really care how much, as long as it doesn't exceed my desired volume of 250. Dissolve that salt in that water, and then stir it up good. Make sure it's all dissolved, and then water down to 250. Maybe invert it once or twice to make sure it's all mixed up good. And also a similar equation I call the dilution equation, and it's called M1V1 equals M2V2, or MCVC equals MD times VD. C stands for concentrated, D stands for diluted. So if I have a molarity and a volume of certain aqueous reactant or whatever in the laboratory, and I want to water it down, could be an acid, could be a salt solution, I water it down, I just add water to it. And when I add water to it, I'm not really adding or taking away any moles. I'm not reacting any moles away. The moles of chemical solute stay dissolved in the water, but I'm just adding more water. So the moles of solute equal the moles of solute in the concentrated version equals the moles of solute in the diluted version, but the molarity will certainly go down. So this molarity is larger, this is smaller. Oh, sorry about that interruption. All right, I'm back. Sorry about that. Yeah, so let's try that a couple times. I could say if I had 10 milliliters of 12 molar hydrochloric acid, which is concentrated hydrochloric, called fuming hydrochloric, that's too concentrated. I take 10 milliliters of it and I want to water it down to 250. What's the new concentration? Well, it's so relatively, maybe I've just done this too much, so it seems simple to me, but I take the 12 molarity times the 10 milliliters right there, and take the new molarity, I don't know what that is, times the 250 milliliters I'm creating by adding, let's see, I'd be adding about 240 milliliters of water to this, would give me 250 milliliters of water, but this new concentration is, of course, less, and so I just take this one times this one divided by this one, and the millis cancel here. Nice to know, nice to use. I don't need to change the milliliters to liters because the milli units cancel anyway. Milliliters cancels milliliter, and I come out with the new molarity. Could also say it this way. Could also solve it this way, and that's to say, wait a minute, what's different? Oh yeah, I could say 12 times 10 is 120 millimoles. So this is 120 millimoles, and this is also 120 millimoles because 0.48 times 250 should give me 120 millimoles. I don't know. Silly. What volume of 5.75 molar NaOH should be watered down to give 750 milliliters of 0.836 molar sodium hydroxide solution? Well, I don't know, but I do know the moment I see the word of right there, I think I want to times in mathematical story problems. Of means times. So I'll take 750 times 8.836 straight away and say that must equate to my new volume times my concentrated base. And so that would be, oh yeah, this one times this one divided by this one comes out to 109. So what I probably would do in a volumetric flask, now 750 mil volumetric flask is kind of rare, but you can find them. They're these weird, sorry about my stupid cartoon, I can't draw, that a weird round bottom, kind of a flat bottom, but bulbous on the bottom. And there's only one mark, and that mark is right there where the 750 mil volume comes to. So these volumetric flasks are super helpful for just measuring one thing, and that's this volume right here. So I would add 109 milliliters of the concentrated NaOH into my flask. I don't know how I'd measure 109 very accurately. I guess a graduated cylinder probably would be okay. A burette would be better. But anyways, I'd add that to the flask, and it would take up just a little bit of space down here, 109 milliliters, and then I'd water it down up to this line. I'd stop right about here and use my squirt bottle to make sure I got exactly to the line, the bottom of the meniscus. Oh, thanks. That went kind of fast, but I appreciate your watching. I'll see you in class. Good luck.